We're live. You excited? I know I am. All right. Okay, so we're just going to go right into it. And then tomorrow we can kind of call it like a review day. This is really the last day of us doing something new in this chapter. And then I'm going to, sync some things together, finish off our historical document that I did way back when I was getting my anger management training, if you remember, which worked for a while. And then, we'll talk historically what happened with all these methods specific to our House of Representatives. And I'll share a document that, of course, I stole offline, off of the online internet. And then I think it's kind of cool what happened. So 2 more methods to talk about. One is Adams. We know who Adams is, John Adams, correct? And basically his method is identical to Jefferson's method, except what? What do you think's different here? You round up. Oh, there we go. Is our little message. I always get that when I do a video. Comes up every time. Anyway, you don't know that. Instead of rounding down, like if we get 13.7 using Jefferson's method, we go down to 13. Webster, how does Webster round? Normal, mathematically. Adams thought, well, let's try rounding up and see what happens. So what happens with Adams is if you get 13.1 as a quota, where does that go? It goes to 14. Just as weird as, Jefferson's method, you get 13.9, you round down to 13. Okay, so what I'm going to do is show you this chart, and then I'm going to, circumvent it, what you should do as a student, and hopefully you feel better about that as we go along. Meaning, this is just a method to help you sink down the numbers where you need to, get them. This is called a divisor method, where you have to figure out the divisor. So if you do a, you do a divisor, the first one, of course, is, in this example, here's the total population, 15,600 is these numbers added together. We're going to give out 40 seats. So the first divisor is total population divided by those 40 seats, and then we check 390. So then what we do is take all these individual populations and divide by 390. Now for purposes of notes, you could just take this down. Of course, I hope more and more people have a graphing calculator, right? If you look at that sheet that you picked up as you walked in, we have a ginormous set of values pertaining to, again, the United States at a particular year. Okay, and then you can see in this first quota that we figure out, 8.33 comes from 3250 divided by 390 here. But then for Adams' method, we round up to 9. 11.9 goes up to 12. That's 4650 divided by 390. 5170 divided by 390. You get 13.2. We round up. Okay, blah, 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 blah. You end up with 42, which is too many. So what do we have to do with this divisor? Do we have to increase it or decrease it? We have to increase this divisor so that when we take these population numbers divided by this increased divisor, these numbers go down. Okay, now, this was just a method. If you wanted, isn't 42 close? Isn't 42 close? And if you had your calculator and you had these numbers typed in the list feature, then what you could do is just modify this divisor and then analyze these decimals until the sum rounded together equals 40 on the dot. So you could guess and check. All you would have to do is tell me what is your modified divisor that you tried. So you might try 400. All right, so if you increase this to 400 and then divide the whole list by 400 and then analyze the decimals. Blah, 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 blah. So the first thing that we do, though, is we take, if you didn't want to do that and you wanted to be, just do what we've done in the past to try to sink down what it is going to be, you take the highest population divided by 12 I'm sorry, I skipped a section there. 13 minus 1, and you end up getting 12 for that. Okay, so then this increases the divisor greatly. Okay, so, again, this is an option. You could, I personally, at this point, after doing this so many times, I wouldn't even do any of this. Okay, what I would do is guess and check. Does everyone understand what I'm saying? Okay, so I try 400, I try 410. It's faster than trying to do this convoluted method of, trying to sink them down. That's all that was there for you, though. That's why that was there, to get you to understand that. So I would have tried 400. It may or may not have worked. 410 is not the only divisor that would work. You need to understand that. This is, there's many numbers that would work that would end up rounding up to be 40. So I think guessing and checking is the best. And then if you would have guessed and checked 400 first, 400 may not have worked, but then 410 does. This list represents when I divided these population numbers by 410, and then we end up getting 40 on the dot. Okay, so Adams' method is identical to Jefferson's method, except for the fact we always round up. And actually, you could say the same thing with Webster. Jefferson rounds down, Webster rounds mathematically, Adams always rounds up. All right, just different ways of looking at these scenarios. The last method, and then again, tomorrow in our shortened schedule, you know it's shortened schedule tomorrow, right? You get cheated a Samulus, sorry about that. You're going to find out that this is the method I think that's used to this day, as far as the House of Representatives, the numbers assigned out. Okay, it's called a divisor method. What a divisor method is when you divide by the divisor and you miss. Well, then you have to modify the divisor. There's no like using Lowndes' method or Hamilton's method, which was just, very basic, very simple. You divided once and then you adjusted the numbers based off of other parameters. A divisor method is if your divisor does not work in the first chance, you have to modify the divisor by some method. Okay? All right. So instead of rounding, this is what you need to do. You compare the quota that's in decimal format. Okay, so you're going to leave the quota as a decimal to the geometric mean of the two integers that quota is in between. Now don't freak out about what geometric mean is. Okay, geometric mean is a simple mathematical concept listed right here in this example. Okay, but before that, M quota, that means the quota that you got. If your quota is greater than the geometric mean, then you're going to assign the larger of the two numbers. Nice little example right here. So let's piggyback off that one real quick. Boom. And you should probably list this right underneath this one. So say you have a population, you divide it by the divisor, and you get 15.54. Before you assign anything, by the way, I like doing this. If it was Jefferson, which would this go to? What would Jefferson do? 15. What would Webster do? 16, because 15.5 mathematically goes up. And then the one you just learned, Adams, what does he do no matter what? Makes it 16 no matter what that decimal is. Well, this is what Hill does. 15.5 is between 15 and 16. Find the geometric mean of 15 and 16, which is just the square root of 15 times 16. So take 15 times 16 and square root it, you get 15.492. Compare the two. Who's higher, the quota or the mean? When the quota is the biggest, you go to the larger integer. So what would the state get, 15 or 16? 16. So it's a little bit more mathematical complication. And this is the method that the United States chose. So probably something mathematically to it that makes it more fair as opposed to the other methods. Then an anti-example of that. Say you take a a state's population divided by the divisor, whatever that may be, and you get 22.129. That's between 22 and 23. Take the geometric mean of that. This time the quota is smaller than the geometric mean. So therefore, we're going to go to 22 on that one. Okay, so much different method, most unique, just something, a pattern that you have to have memorized. So when you're actually building your chart, you need your quota as a decimal listed, and then in the next, right next to it, you want the geometric mean listed right next to it. Then you can make your comparisons as far as which one do they get. The problem with this is when you assign the final number, that number has to hit right on the dot. What if it doesn't? What if your sum doesn't equal what's given out? What do we have to do? Do it all over what? Again. And it's a divisor method, so you have to modify the divisor in order to get this to happen. Probably be kind on a test that you'll, if it doesn't work the first time, it'll at least be close so that you can modify the divisor maybe only one more time because this one does take a lot of work. Okay, so again, my role just to kind of, circumvent what's happening in this list. You have 23 new nurses to 6 hospitals, and here are the, I guess, average population of patients or what they can actually hold, blah, 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 blah. So step 1, sum them up. Add them up, and then divide by how many nurses you're going to apportion. And you get the standard divisor of 204.04. Take all of these individual populations and divide it by that 204.04. Now, write the decimals down for those quotas. And this is where it gets to be a pain. What you need to do next is, right next to this quota, is find all the geometric means of what these decimals are between. So 1.4 is between 1 and 2. The geometric mean is 1 times 2, square root that. Same thing with this one. 7.44 geometric mean, 7.44 is between 7 and 8. 7 times 8, and then the geometric mean of that, so on and so forth. So zoom in on that little area so that you can have a good chance of writing that down well. Maybe one more time, and then don't look at the blue. Okay, now kind of giving you a chance to catch up a little bit, blabbering more and more here. Make your comparisons correctly here. What's 1.451 compared to 1.414? Bigger or smaller? What's this compared to this? Bigger. So when the quota is bigger, you go up. When the quota is smaller than the geometric mean, you round down. 7.44 compared to 7.483, smaller, round down. 6.3, 6.4, smaller, round down. Smaller, and so close, but smaller. Okay? So, this is how you make these comparisons. You got to go along the lines. The math is not hard. It just takes some time. That's it. All right, so now let's look at what we have here. We only gave away 22. How many were we supposed to give away? 23. Are we close? Yes or no? We're close, but we're too few. So what should I do with this divisor? What should I do with this number right here? Should I increase it or decrease it? Should I increase this divisor or decrease it? If I increase the divisor, what do these numbers do? They go what? Smaller. What do I want them to do? Get bigger. So since I am close, I think I would have made a management decision. I would have not done that highest population divided by, a number that's smaller. I would just adjust this number. So I want these to go up, so I need to make this divisor go down. Look at what ends up winning. Okay? So I think we could figure out that 204.04 came so close. I mean, look at this. 2.446 compared to 2.449. That was almost a win. That was almost this going up. So that even proves how close I am to giving away 23. So my divisor needs to be decreased, but not by a whole lot. So probably 203, maybe even 202, maybe even 200 would have won. All right, as far as getting this done. When you have your calculator, you can go ahead and do those numbers real quick, divide a whole list, guess and check, and then of course answers will vary. So we don't really, I want you to be able to not have to write this down a whole bunch of times. I would like you to be able to figure this out by analyzing how actually close you are and then modifying the divisor on your own, not being stuck to some sort of thing that I taught you from before. Think about it, okay? So this list over here is dividing by 203, these numbers. So 204.4 just missed. Rationalize. Go ahead and do this. Maybe on your own, actually you can look at this. We could use these over here already because this one's 1.458. We already did that geometric mean. This one's between 1 and 2 again. This one's between 7 and 8 again. 6 and 7, 4 and 5, and 2 and 3. So I could take these numbers and compare it to this geometric mean that I've already done. So the only time you really have to redo the geometric mean if a number really switches from 3.9 to 4.1, let's say. So my geometric mean numbers are already there for these, and I can make that comparison. And yes, of course, this is the one that bumps up because it was already close to begin with. Right there. Does that make sense? Okay, so guessing and checking as far as this is concerned, I don't really think you have to do geometric mean more than once, except maybe if one number flips from 3.9 to 4.1, let's say. Okay? All right, so hopefully that makes sense, and that's what we're going to do with it.